For problem number 5, we are working with a capacitor and resistor in series with a switch, and we are given the equation for the current as a function of time, which we know as the positive charges move onto the capacitor. These positive charges are going to counteract the charge of the battery, and it causes the current to slow down. It's kind of creating a resistance. So in order to determine the EMF of the battery, the full charge of the battery, we're going to take into consideration the fact that once the switch is closed, at the moment the switch is closed, the current traveling through is at its maximum. So it is as if the capacitor is not there. It is only once it starts building charge that we start experiencing a decrease in current. But in order to get the full EMF, we need to treat the circuit as if the capacitor isn't there and it is just a circuit with one resistor. The resistor is 4 times 10 to the 6 ohms, and we have a maximum current, which our maximum current is always the constant that is in front of our current versus time equation. So in that scenario, the maximum current is going to be 5 microamps. So in this scenario, we are going to use the equation where EMF or voltage is equal to our current times resistance. Our current, again, is 15 times 10 to the negative 6 amps, and our voltage is 4 times 10 to the 6 ohms, and that gives us a voltage of 60. Okay, so from there, and I'll go ahead and write this in our equation. From there, we need to develop an expression for the charge on the capacitor as a function of time. So what we know, and this is in our equation sheet, that current is equal to change in charge over change in time. So the amount of charge that flows over a certain amount of time. In this scenario, I have an equation for the current with respect to time. So if I rewrite this, dq is equal to the equation for current, I naught E to the negative t over 8 with respect to time, which is dt. From there, obviously, we've got dq on one side, dt on the other. We can take the integral. For the left side, it's from 0 charge to charge q. And then from the right side, it's from 0 charge to some arbitrary time t. This is easy because the integral of dq is just q. It's actually q minus 0, but the 0 obviously eliminates. And then here we've got I naught. I'm taking the integral of e with respect to t, so that's just e to the negative t over 8. And you have an equation, general equation for this in your equation sheet. But then we have to divide it by the derivative of our function in the exponent. So the derivative of negative t over 8 is negative 1/8. And then we're going from t to 0. So this should be I naught. Let's simplify this out. I'm going to multiply by the reciprocal in the denominator. Q is equal to negative 8 I naught times e to the negative t over 8 minus e to the 0, because negative 0 over 8 obviously cancels out. This equals 1. So I get q is equal to negative 8 I naught. I get e to the negative t over 8 minus 1. This is our final equation, although we can clean it up a little bit. If I take my negative and distribute it to each part of my function, then I can get rid of the negative in the front. And q is equal to 8 I naught times 1 minus e to the negative t over 8. Now, in this scenario, the negative e to the negative power is going to have a upward increasing graph. And generally it increases to 0, but because we added 1 to it and we're multiplying it by 8I naught, it actually increases to some value of maximum charge. That maximum charge here is this right here. So this is 8I naught. And you can calculate that value if you'd like to. We're given the fact that I naught is equal to 15 microfarads. In the answer key, I don't know why they do this, but charge is equal to voltage times capacitance. And voltage, again, is another variable for epsilon, or our EMF, electromotive force. So they substitute EC in for the Qmax, but the numerical value is in the equation anyway, so I don't care how you represent it. Okay, so in the next part of this problem, we're determining the capacitance of the capacitor. What we do know is that our maximum charge is equal to 8I. We know that our maximum voltage is equal to 60, which we got in part A. And we want to know the capacitance. So C is equal to charge over voltage, or epsilon, which is 8 times 15, times 10 to the negative 6, all over, this is our I naught, 60 volts. And in the end, we get a charge value of 2 times 10 to the negative, a capacitance value of 2 times 10 to the negative 6 farads. So that would be part D.